All right, hi everybody. We're about to get started with trivia in just a moment here, but since I see some people trickling in still, I want to make sure that everybody who wants to join us for trivia has a trivia sheet and a pencil or a pen. If you still need one, go ahead and come up to the front here, or just raise your hand. But it looks like you're coming up to the front, so that's even easier. Thank you. And with that, we're going to get started with trivia. So go ahead and pay attention to the screen up here. We're going to spend about 30 or 40 seconds on each question. If that feels a little bit fast for you, that's okay. We're going to wrap them, and we're going to go back through again before we actually get started. So go ahead and yeah.
Okay, so that was the first round through the trivia questions. Now I'm going to go back and go through them all again, but this time only give you about 15 seconds per slide, so you can like check your answers, get any questions you missed, etc.
All right, that's it for trivia. So if you missed anything, let us know right now. We'd be happy to run back to a slide real quick if anybody has any they need to check again. But otherwise, go ahead and bring your trivia sheets and your little golf pencils up to Sam over here. And we're going to get those graded during the first talk. And in the intermission between talks, we will announce the winners. And then the winners will, after the second talk, be they'll come up here and collect prizes because we have prizes.
Okay, so now it is my pleasure to introduce our first speaker. It's going to be Lucas Pfeiffer. He is a PhD student in the University of Washington's Earth and Space Science Department. He works with Dr. David Catling. And he's going to be talking to you guys today about using icy eruptions to look for life in Enceladus' unseen ocean. So now I'm going to invite Lucas up to give his talk.
All right. Hello. 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 Can you hear me okay in the back? Is this okay? Louder? A little louder? How about now? Is this any better? Okay. Good? Testing, testing. Good. Okay, awesome. I'll try not to turn away from the mic. So, hello. My name is Lucas Pfeiffer, as Megan said. And today I want to tell you this little story about icy eruptions on Enceladus and what they can tell us about life in an ocean under the surface on Enceladus. So before we journey out to the outer solar system, where Enceladus resides, let's take a moment here on Earth. And I'd like you all to imagine if you went down to the coast and stood in the shallows of the Pacific Ocean, and you brought a bucket with you, and you use that bucket to scoop up some water from the ocean. Now, how much life do you think would be in your bucket? So maybe you get lucky and you find a small fish swimming around at the bottom of your bucket. Maybe you find a loose bit of seaweed that a wave carried into your bucket. But what about all the life you don't see? So in an average bucket of ocean water, there are over 10 billion bacteria and over 100 billion viruses. So even when we don't see it, the oceans of our planet are teeming with life. So what about on other worlds? Could oceans on other planets or moons in our solar system be a good place to look for life too? Let's try and answer this question. So our nearest neighbor is the moon. This is a real picture of the moon, by the way. It's taken from the International Space Station. And our moon, Earth just has one moon. It's rocky and dry, and unlikely to have any life there beyond what humans bring there. But we can look a little further out in our solar system to the planets we call the gas giants, Jupiter and Saturn. And these giant planets have many moons, about 60 each. And many of these moons have liquid water, not on their surfaces, but underneath their surface. So here is a 3D model of one of these moons. Europa is a moon of Jupiter, and you can see Earth down here for a size comparison. And Europa has this thick outer layer of ice, and underneath that ice is a deep ocean of liquid water. And it's kind of hard to see just how deep it is from this picture, but the ocean of Europa is about 10 times deeper than even the deepest parts of Earth's oceans. There's a cat. So unfortunately, with Europa and moons like it, it's really difficult to see what's going on inside them. So these outer layers of ice prevent us from observing the ocean directly. Someone else found the cat. So it's really difficult to see inside these oceans. We can't use telescopes from Earth to observe the oceans directly. Even if you landed a spacecraft on that surface, you'd still face the problem of drilling through miles of ice just to get down to the ocean. But there's one moon in our solar system where this outer layer of ice isn't a problem. So Enceladus is a small moon of Saturn. You can see just how small it is here in comparison to Earth. The distance from its north pole to its south pole is about the same as the distance from San Francisco to LA. And for a while, there wasn't much that we knew about Enceladus, other than the fact that it had this unusually bright and white surface. And no one was really sure why that was the case. That is until the Cassini Mission. So the Cassini Mission was a joint mission between NASA and the European Space Agency, where they sent this spacecraft with no people on board out to Saturn to investigate the ringed planet and its many moons. I'm going to show you a few pictures from the Cassini mission. There are so many more, so next time you're bored at your computer, please Google just NASA Cassini images. You'll find so many. This is sort of the north side of Saturn. You can see it being lit up by the sun. It's casting a shadow on some of Saturn's rings in the background. And at the north pole of Saturn is an enormous hexagon-shaped storm that's several times the size of Earth. So pretty wild to think about. Here is another Cassini image. This is a close-up of some of Saturn's rings and one of Saturn's smallest moons called Daphnus over there on the right. It's only about 5 miles across. And its orbit is within some of Saturn's rings, which you can kind of see here. Oh yeah, it's not showing up great, but there's like rings above where the moon are as well. And because Daphnus' orbit is within its kind of ring structure, as it goes along in its orbit, it creates these interesting wave-like disturbances in the ring particles. Here's one more Cassini image. You can see Saturn in the background, and you can hopefully make out in the foreground. This is Saturn's largest moon called Titan. Titan is the only moon of Saturn that's large enough to hold on to an atmosphere. So you can see its kind of hazy atmosphere right here. Titan's a really interesting moon in terms of looking for life, because not only does it have an ocean underneath its surface, just like Europa, it's also got this atmosphere, and it's got liquid on its surface, not liquid water, but lakes and seas of methane and ethane. So it's a really cool place to think about life that could be very different from life on Earth. So Titan deserves its own talk, but I want to focus on Enceladus for tonight. So when Cassini turned its attention to Enceladus, it found something really surprising, which was huge eruptions coming out from cracks in the surface of Enceladus near the South Pole. And these were shooting out hundreds of miles into space. And so what was only at first a small part of Cassini's planned mission, it became a top priority to get a closer look at these eruptions. This is another actual picture from the Cassini mission. This is the surface of Enceladus, and you can actually kind of make out the cracks where these eruptions are coming out. And Cassini didn't just take pictures of these eruptions, it actually flew through them and measured the different chemicals there. And what Cassini found is that these eruptions are mostly made up of gas, such as water vapor. So you can kind of think of these eruptions as like huge jets of cold steam. And being carried along in this gas, there were also little particles of ice. And these ice particles contain salts and some organic molecules. And organic molecules, that doesn't necessarily mean they don't always have to come from life. They just have carbon in them. But organic molecules are like the building blocks of all life on Earth. So definitely exciting to find here. These icy particles are also interesting in that they're what help us see these eruptions in the first place. In this image, you can see them glinting in the light of the sun. And they're also what's responsible for Enceladus's bright white surface, because while some fraction of these eruptions escape from Enceladus's gravitational pull, and actually some of that material is what supplies the E ring, if you got that trivia question right. Some fraction of the eruptions kind of snow back down onto the surface and give Enceladus its nice fresh white coating of ice. So here's one more image of Enceladus from the Cassini mission. You can maybe make out another of Saturn's moons in the bottom right over there. That's Pandora. And then some of Saturn's rings in the background here. And again, we see these strange eruptions of ice and gas coming from the south pole of Enceladus. And at first, it wasn't really clear where exactly these eruptions were coming from. So some people thought that maybe this was gas being released through cracks in the surface, and that the little ice particles were getting kind of swept up in that gas, kind of like sand whipping through the air on a windy day at the beach. But then when it became clear that there was salt in them, well, that was kind of surprising, because salt and ice don't play well together. If you had, say, a cup of salt water and you froze it, you got it cold enough to freeze, the salt would tend to stay behind in the liquid water, and the ice that forms would tend to be pure ice. So salt mixed in with ice here had to mean that these ice particles weren't coming from a pure ice surface. They had to be coming from a liquid water ocean that had salt in it, somewhere below the surface. And at first, it seemed like maybe this ocean was only near the South Pole where these eruptions were happening, but then some scientists noticed that Enceladus wobbles a little bit as it moves in its orbit around Saturn. And so this means that basically its outer icy shell and its rocky core seem to move separately from each other. If the ocean looked like this, if it was only near the South Pole, then you wouldn't expect that behavior because the core and the ice shell would be more or less connected everywhere, or almost everywhere. So you would expect them to move rigidly. So the fact that you observe this wobbling has to mean that the ocean under the surface is everywhere under the surface and sort of separating the core from the ice shell all the way around. So now we see why Enceladus is unique. It's the only moon in our solar system and the only world apart from Earth where we can get a taste of an ocean from the surface. We can't get a bucketful of the ocean water directly, but we can get a bucketful of these eruptions. And we can begin to ask, could life exist inside this ocean? And by extension, could life exist inside other icy moons where we aren't lucky enough to have these eruptions? And while we haven't found any direct evidence for life yet, we do have a pretty good idea now of what kinds of life could survive there. So there was no oxygen measured in the eruptions. And since fish need oxygen to survive, you're probably not going to find any Enceladian sea bass. And because the ocean is underneath miles of ice, there's no sunlight down there. It's pitch black, which is pretty creepy to think about. So plants like seaweed, which need sunlight to survive, they're out of the question too. But bacteria and microbes, some of them can get by just fine without oxygen or sunlight. So could they exist in Enceladus' ocean? Well, maybe. So there's one type of microbe in particular, and this exists on Earth. We see them especially around hydrothermal environments, which are these warm areas of the seafloor that are heated up by magma beneath the seafloor. And these microbes use a couple of gases. So they use hydrogen, which is a gas we used to use in airships with mixed success, and carbon dioxide, which is a gas that we breathe out. And they use these two gases together to make methane, which is a common natural gas on Earth. Now, all three of these gases were measured in the eruptions, which is pretty cool. I think this begs the question, is there enough in the ocean for microbes to actually use? Well, at this point, it's important to remember that what we're seeing is not the ocean itself. We're seeing the aftermath of some complicated eruption process. And we're trying to make guesses from that eruption about what it was like at the beginning in this ocean. So I think looking at the eruptions and to make guesses about what's going on in the ocean is a little bit like looking at a cake and trying to figure out the ingredients. And in this case, you're not allowed to ask for the recipe because it's buried underneath miles of ice. So what a cake looks like and tastes like depends not just on the initial ingredients, but also the conditions under which it was baked, like how long it was in the oven and the temperature the oven was set to. In the same way, what we see in the eruptions, the chemicals we find there, are a product of not just what you started out with in the ocean, but also the processes that brought them up to the surface and may have changed them along the way. So that's what I focus on in my research. It's trying to understand the steps on this journey from ocean to eruption. And yeah, I forget what I was going to say next. Oh yeah, and how this icy, gassy stuff gets changed along the way. So let's take a closer look at the journey of that eruption through a crack in the outer ice layer. That's where we're headed. Okay, so this is a diagram, a drawing of a close-up of these ice cracks. You can see the eruption coming through that crack, originating from the ocean that's sort of underneath the ice and partially filling the cracks. So one of the first questions you might ask at this point is, why is this eruption happening in the first place? Well, Enceladus is such a small moon. It really has, gravity is very weak there. So Enceladus has a lot of trouble holding on to any sort of atmosphere. This means that the surface and water that fills the cracks in the surface is basically being exposed to the emptiness of space. Sometimes we call that the vacuum of space, and that's really an appropriate term here because it acts like a vacuum cleaner and sucks out water and whatever else is in the ocean and creates these eruptions. As water is sucked out of the ocean, it gets turned into water vapor, and other gases that are in the ocean, they can bubble out as well, kind of like a soda going flat or a beer losing its bubbles. But water vapor will come, or water will come out of the ocean faster than other gases come out. And even between the other gases, there can be differences, like between carbon dioxide and hydrogen. And so generally, gases that come out faster, you'll tend to see more of them in the eruption. They'll be kind of overrepresented. That's not the end of the story, because as the eruption continues upwards, it gets colder and colder, so cold that some water vapor freezes onto the walls of these ice cracks. It's the same process by which you sometimes get ice building up in your freezer. The walls get so cold that they pull moisture out of the air and ice builds up. It doesn't get cold enough for other gases to freeze out like that. So water vapor is the only one that's affected. So how do we know that all this is happening? There's no real easy way to see this happening, even in the Cassini images. But yeah, especially what's going on down at the bottom of these fissures. These are, it would be miles down from the surface to this water. Yeah, what I was gonna say. Yeah, basically it's hard to see down. Oh yeah, these cracks are very narrow. So they're maybe only like a couple feet wide, maybe even narrower. So it's like trying to see down this very narrow ravine. All hope isn't lost though, because while we can't directly see these eruptions beginning to form, we can recreate a little piece of that process in the lab. So that's what I try and do with this experiment, which is one part of my work. Down here is a stainless steel cup. It's, for context, it's about the size of a can of beans. And inside I put water that represents Enceladus' ocean. And then that pipe going over to the right will lead to a vacuum, so I can remove gas from this cup and make it so that the area above the water is empty, just like outer space. That handle up there just lets me open and close that pipe to the vacuum, or I could switch out the vacuum for a tank of gas, and I could introduce some gas into the system that I want to measure. Finally, the device up at the top just measures the pressure in this cup, so it tells me the amount of gas in the space above the water. And that is connected over to a computer, so I can keep track of how that amount of gas changes over time during an experiment. And I'll take you through what it's like to do one of these experiments. So here's a close-up of that cup of water. So at the beginning, the first thing we need to do is turn on the vacuum to get rid of any gases that are already in there, because there'll be some gases inside from our own atmosphere. And oxygen and nitrogen, which are common gases in our atmosphere, they weren't measured in the eruptions, so we don't want them in our experiment. So we use the vacuum first to get rid of those gases. And then we add in a gas that we did see in the eruption, so maybe methane. We add this methane to the cup, and at first it's sort of floating around above the water, but if you give it enough time, gas will dissolve into water, just like you can dissolve sugar or salt in water. And over time, it'll begin to dissolve and eventually create this kind of balance between the gas above the water and the gas in the water. So now our homemade Enceladus ocean is ready. It's got gas in it that we've seen in the eruptions, and we just want to measure how fast it would come back out. So we use our vacuum once again to remove the gas from above the water, and now we've created our own miniature version of the vacuum of space up here. And now we quickly turn off the vacuum, and gases will come out into that empty space and try and create a balance once again. And as that happens, we will use our trusty device for measuring the amount of gas above the water, and we can see how it increases over time. And just by looking at the curve of the graph that we get out, we're watching how fast gases are coming out of this water. So with just a cup of water and a vacuum, we're able to measure how fast these gases would come out of an ocean on an icy moon that's almost 1 billion miles away. So that's one part of the story. What about the second part I mentioned earlier, where water freezes out onto the ice, the cracks in the ice shell? How do we know that this is happening? Again, there's no real easy way to see this happening, but there's one reason we know it should happen, and that's based on the temperature of these icy walls. So Cassini was able to measure the temperature of the surface of Enceladus, and near these cracks, the temperature is right around minus 100 degrees Fahrenheit, which is about the same as the coldest temperature ever recorded on Earth, somewhere in Antarctica. This is actually one of the warmer spots on the surface. Further away from these cracks, the temperature goes down to like minus 300 degrees Fahrenheit, so kind of unthinkably cold. We can't directly measure the temperature down at the bottom of this crack, but we can use what we know about the freezing point of water to figure out that temperature. So water freezes at a temperature of 32 degrees Fahrenheit. So if you put ice in contact with water, whether that's ice cubes in a glass of water or an iceberg in the ocean, the temperature of both the ice and the water shift to right around 32 degrees. So from that, we know that where this ocean is in contact with the ice walls, the temperature should be right around 32 degrees. So I mentioned earlier that because these walls get colder towards the surface, some of the water vapor freezes out onto the walls, building up like on the walls of a freezer. And this happens all the way up along the eruptions journey. But we want to try and figure out exactly how much water gets lost to the walls during that process. So to do that, we use equations that represent the freezing process and equations that represent the plumes for this eruption and its upward motion. And we try and calculate exactly how much water goes missing. So what we're really trying to answer here is how difficult is the journey for water vapor? And that depends on two things. That depends on, first, how deep this crack is, and second, how wide it is across. So if you have a very deep or narrow crack in this ice shell, then water vapor has a very long and difficult journey. There are plenty of opportunities for it to run into the ice walls and freeze onto them. But on the other hand, if you have a very wide or shallow crack, then the water vapor, it's just like a short trip down an empty 10-lane highway. Lots of water vapor can survive that journey to the surface. The trouble is we don't really have a good handle on the size and shape of these cracks in the ice shelf. They could be a mile deep or 5 miles, or maybe 10 miles down to the water. They could be very narrow across, like only an inch or maybe a foot, or the largest we expect from images of the surface is that they could be about 10 feet across. So to try and take into account all these possibilities, we run our models for a bunch of different widths and a bunch of different depths. And one of the ways that we can check to see if a particular model is realistic is we can see how much of an eruption it would produce. And we can compare that to what Cassini saw in those images. So compared to a narrow crack, a wider crack might create too much of an eruption, more than what we saw in the images, so we can rule out that model. Or if you had a very deep crack, maybe so much water vapor goes lost along the way that you're only left with this little wisp of an eruption that's less than what we saw in the images. We could rule out that one as well. So with all that, we now have a pretty solid understanding of what it takes to go from an ocean to an eruption. We've used a homemade ocean in a cup and some knowledge about the physics of ice and water vapor. So now we know which gases come out fast, which come out slow, and how much water goes missing along the way. So we can taste our final product, the eruptions, and make some pretty good guesses about the ingredients that we started out with in the ocean. And importantly, how much of these ingredients there are. So from this work, what we found is that there should be quite a lot of hydrogen and carbon dioxide and other gases in the ocean. So much so that this ocean is probably about as bubbly as a soda. And that's not at all an exaggeration. So there's plenty of gas for microbes in the ocean to potentially use. You could also say it's about as bubbly as a beer, which brings me to a very exciting announcement I'd like to make. This is very much not a real thing, but we're collaborating with Bickersons Brewhouse to develop a beer that has all the tastes and chemical qualities of Enceladus' ocean. So you can look forward to a beer that is undrinkably salty. It's not as bad as Earth's oceans, but if you can imagine like 1 part ocean water to 2 parts fresh water, still pretty gross. If the salt doesn't kill you, then don't worry, because the ammonia definitely will. we think there should be a lot in Enceladus ocean, so we're adding it to our beer. It also give it a nice aftertaste of window cleaner. And then lastly, instead of doing the traditional carbon dioxide bubbles or nitrogen bubbles like in a nitro stout, we're opting for the full suite of gases that are in Enceladus ocean. So that includes hydrogen and methane. So I should warn you not to open these near an open flame, or you'll have a miniature recreation of the Hindenburg on your hands. But in all seriousness, while this sounds terrible to drink and probably legally poison, a lot of these qualities are not necessarily bad for other types of life, and in some cases are actually beneficial. I mean, you wouldn't want to go and drink ocean water on Earth either. So salt is no problem for aquatic life on Earth. Ammonia, while that can be toxic at some levels, ammonia is also a really important source of nitrogen, which is a key nutrient for all life on Earth. And hydrogen, you already know, hydrogen is a source of energy for this type of life that could be on Enceladus. And that type of life produces methane, which is also measured in the eruptions. So all in all, Enceladus is a really good place to find life because there is energy for life in the form of this all-you-can-eat gas buffet. There are the building blocks of life in those organic molecules I talked about earlier in the icy particles. In addition to those organic molecules, or in some cases within those organic molecules, we've actually detected all 6 of the most essential elements for Earth life. They were all detected in the eruptions of Enceladus. So carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur were all detected. Not only is Enceladus a good place for life to exist, it's also a great place to go looking for life because these eruptions are bringing samples of the ocean from that ocean up to the surface and beyond, where we can actually measure them. So that brings me to my next slide. Excitingly, recently, this mission called the Enceladus Orbilander was prioritized for, it's the number 2 priority for the next big NASA flagship mission. So that's a lot of words, but basically it's really good news for a return to Enceladus and following up on where the Cassini mission left off. And this mission is called the Enceladus Orbilander because it would have 2 phases to its mission. The first phase is an orbital phase where it would do something kind of similar to what Cassini did, where it would fly around Enceladus and fly through those eruptions again, but this time with bigger and better instruments to make, help us find out even more about what's going on in those eruptions. And then it would have this second phase where it would land somewhere on the surface, somewhere near the cracks where those eruptions are coming out. And this lander could scrounge around for things that had already fallen out of the eruptions, or maybe even catch particles as they snow back down to the surface. With this improved suite of instruments compared to what Cassini had, the Orbilander would not only have a better chance of detecting molecules that may be produced by life, it could also look for life itself, like microscopic life that could be preserved in those little ice particles, frozen in place in those little droplets of what was once Enceladian sea spray. So, what do you think? If you traveled 800 million miles out to Enceladus and you brought a bucket with you, and you used that bucket to scoop up some of the eruption from that strange, salty, soda-like ocean, how much life do you think would be in your bucket? Thank you.
All right, thank you, Lucas. Okay, we have time for just a few questions here. We'll probably do 2 or 3 of them, depending on how fast that goes. So if you have a question for Lucas, go ahead and raise your hand, and I'll let Lucas step back up to the mic and answer any questions.
Yep, okay. No, yeah, that's good. Yeah, so everyone can hear the question. The question was, what causes the ice to crack in the first place, and do they eventually seal up? Could they form somewhere else? we don't know exactly why the cracks start in the first place. But what we do know is that the ice shell of Enceladus is thinnest at its North Pole and its South Pole. So that explains why these eruptions are at least happening at the poles, but then why is it only happening at the South Pole? That's still an open question. People think maybe there was some event in the past, some kind of thermal event under the surface that started these up. And I think there's been some modeling work to suggest that once you kind of get these started in one place at one pole, it's really hard to get them started at the other pole because it's just kind of, there's more flexibility in the whole ice shell, I guess. Yeah, but they could definitely be sealing and reforming over time. I think there's also evidence that like the cracks used to be cracks at like different orientations just in terms of like their angles, but still all at the South Pole. Yeah. Let's go hand over here. Yeah. Oh, that's a good question. How old is the ocean? We don't know. So we don't even really know how old the whole moon is. So it could be like age of the solar system. So that's 4.5 billion years. So that would be like similar age to Earth. It could be way younger. Some people think it could be like only 100 million years old, but we really don't know right now. Yeah, good question. Yeah, sure.
Where does the energy come to form these spouts?
Where does the energy come from to form what?
Spouts.
Oh, yeah. So, yeah, I guess you can think of, because this water is kind of just being exposed to the vacuum of space, it is just getting kind of pulled out from there. There's also been some suggestions that maybe this energy has to do, this kind of comes originally from tidal forces, because basically the force of gravity from Saturn is quite strong. It's kind of twisting and stretching and squishing Enceladus. This is probably why this ocean exists in the first place. As you squish and stretch the core inside Enceladus, it's creating heat and melting ice and allowing for this ocean to exist. So maybe that tidal energy is connected as well, but could just be kind of opening up the ocean to the vacuum of space and letting it go. Yeah. Yeah.
Of the 6 basic building blocks for life, the sulfur question mark. Make the question. Why is there a question mark?
Yeah. So why was there a question mark next to sulfur? Why was that the only one of the 6 elements that had a question mark? Yeah, so I mean, we really, Cassini wasn't, I mean, remember Cassini went up without even knowing these eruptions existed. It was pretty well equipped for, I mean, it did an amazing job for what it could do, but yeah, we only really have confirmation of like 4 gases, apart from water vapor, that are there. So that's carbon dioxide, hydrogen, ammonia, and methane. But hydrogen sulfide, which would be something that contains sulfur, that's like an ambiguous, like maybe it's there, we're not really sure. But with something like the Orbit-Lander, maybe we could get confirmation. Yeah.
All right, let's do one last question. Is this? Sounds kind of weird, doesn't it? All right, well, let's do one last question, and then we'll move on with trivia announcements.
Yep.
Eruptions is mostly water vapor and some gases. Are there other maybe more interesting gases or chemicals in the ocean that would not make it through an eruption?
Yeah, that's a great question. So yeah, could there be other more interesting gases that don't even make it out of the ocean? I think they probably would make it out of the ocean because most gases like are pretty volatile. They don't really like staying in this dissolved state. If they're open up to the ocean, they should get out. I think maybe it could still be really difficult to see some of those though if they're only present at really like small abundances. Yeah. So yet another reason why we need another mission to go back with better resolution.
All right, thank you all for your questions.
Thanks.
Give Lucas another round of applause. Yes. Great talk, Lucas. I'm going to switch over to this mic. That sounds a lot better to me. All right, so we have some trivia. Well, we have a trivia winner, and then we have like a lot of people who got 6 out of 10 right. And Ds may not get degrees, but they do actually get trivia prizes. So I'm going to announce first all of the 60 percenters, and then I'm going to announce the big winner. And then if you win at trivia, sit tight, because after the second talk, we are going to let you come up and choose your prizes. And we're gonna let the 8-point winner, the 80 percenter, choose their prize first, because that's their right as the actual winner. And then all you 60 percenters can come up and pick from what's left. So starting out here with 6 out of 10 correct, we have Enceladus, and C is S-E-A, like Seattle, or like the ocean or something, or like the airport. All right, great job. Yeah, and I do want people to like raise their hands or like shout out or something when they win, so that we know who it is and we can all applaud them and be very impressed. All right, the next trivia winner is their team name is Team Name. So with they get no applause for creativity, but oh, okay. What? Okay, they actually got different ones correct, so we will let them choose their own prizes. I was going to say that's only one prize if you got like the exact same one prize, but yeah. All right, we've got SBP Curly Hairs. Nice. Oh, okay, I get it now. Sky Car. All right, great job. Up front here. And Joe Boat. Nice, well done. And the last 60% winner is Thea and Mark. All right, great job, all of you. I know 6 out of 10 doesn't sound great, but it was in the context of this trivia, which was apparently pretty hard. So pat yourselves on the back. And then the big winner, drum roll. Oh, okay, stop, you're scaring the cat. Okay, the big winner is Dan. Well done, Dan. All right, so just sit tight, and we're going to have you come up and collect your trivia prizes after, sorry, Dan, after the last talk, just so we're not crowding up here right now. Right now, we're going to have about a 5-minute intermission, and then we're going to introduce our final speaker of the night. So go ahead and get another beer. Maybe it'll be a 10-minute intermission, so you have time to get in line and get another beer and all that stuff, get some food if you need, and we'll be back in just a few minutes. Thank you. All right. Hi, everybody. I know you're probably not all back from getting beer yet, but those of you who can hear me are. I messed up. I forgot to go through the trivia answers. So you know who won, but you don't know why it's not you. So I'm just going to run through those real quick so that it's not a mystery. So question 1. Which early 20th century astronomer promoted the idea that Mars' surface had canals on it? That is Percival Lowell. This is like a little preview of next month when we're going to have a bunch of astronomers from Lowell Observatory here, so you can look forward to that. Yeah, A, Percival Lowell. How long ago was Mars thought to have liquid water on its surface? The answer is approximately 4 billion years. Andrew, what's your precise answer?
About 4.
About 3 to 4 billion years, but it clearly rounds to 4. So, Viking 1 found proof of civilization on Mars. Which of the following Martian rock formations has been claimed to be proof of the work of an intelligent civilization? That is obviously the Starfleet logo. Oh, there's a knot in there, so it's not the Starfleet. Everything else has. I'm going to make the claim right now, though, that it's the Starfleet logo. So this question is now incorrect. The highest surface temperature in the Martian summer is equivalent to the average high temperature in Seattle during which month? And the answer is June, 71 degrees Fahrenheit. Saturn's icy moon Enceladus is only 1/7 the diameter of Earth's moon, or about how many miles? So if you do that math real quickly, it's obviously 300 miles. The Cassini Mission's observations of Enceladus and its geyser-like plumes provided evidence of cryovolcanoes, a subsurface ocean, and hydrothermal vents, which you just learned. I guess. Did you? I don't know if we exactly touched upon this question, but true or false? Enceladus's plumes supply the material for Saturn's outermost ring. You did just learn this one. The answer is true. Number 9, scientists have used Antarctica as an analog to study which phenomenon in Enceladus? And the answer, again, is all of the above, because whenever all of the above is an option, that's obviously the answer. And the final question, a proposed mission to Enceladus, the Orbalander, would include how many different instruments to robustly detect possible signs of life? This is kind of just a guess a random number question. So if you got this one right, congrats, the answer is 6. If you actually knew that somehow, then that's excellent, and you probably worked for JPL or something. Okay, great. So now you know why you won or why you lost or whatever. So I am going to hand the mic back over to Megan, who is going to introduce our final speaker of the night in just a moment here.
Switch with that. I have one.
Oh, you have one.
Okay. Okay, so it is my pleasure to introduce our final speaker, Andrew Shumway. He also works with David Catling at University of Washington's Earth and Space Science Department, and Andrew and Lucas, of course, are both a part of the University of Washington's Astrobiology program. And so with that, I'd like to invite Andrew up here if he's done fiddling with the mic. All right, we're good to go. So everybody welcome Andrew Shumway.
Thanks for that introduction. So, I want to pretend for a moment that I am a billionaire CEO of a space travel company. And to thank you all for coming to my talk, I am offering each of you a ticket to visit Mars on a spaceship that I've built that can safely transport humans from Earth to Mars for the very first time. So just by a show of hands, how many people would like to join me for a few weeks vacation on the Red Planet? No, it's just a vacation. You'd come back. Okay, so maybe not everyone's convinced, and for good reason. Mars is not an extremely hospitable place. And to explain some of the challenges that humans would face on Mars, let's go down to the surface. Welcome to the surface of Mars, where for most of the year, the temperatures are colder than Antarctica. There's no oxygen for you to breathe, and in fact, there's very little air at all. And because there's no oxygen, there's no ozone layer to shield us from the harmful UV radiation from the sun. Meaning a few minutes outside without a spacesuit on, you would get a severe sunburn, and longer exposure could lead to more severe consequences. But there are some workarounds to get around some of these hazards. For example, we can build structures or wear a spacesuit to protect us from the sun's UV rays, to keep us warm, and to provide us with oxygen to breathe. But there's still one challenge that we just haven't figured out yet. And that's one of the most important ingredients for life. We just heard a lot about it from Lucas's talk. Where is the water? Where are we going to get water on Mars? So I hate to break it to you, I'm not actually a billionaire. I'm a grad student. So I don't have a ticket for everyone to go to Mars or a rocket ship. So why am I asking these questions? The reason is one day humans will go to Mars. And when they get there, they're going to need water to survive, to drink, to water crops, to take showers and stuff like that. And water is extremely difficult to transport because it's so heavy and it just costs a lot of fuel to move it from one planet to another. So it would be great if when we get to Mars, we can find a source of water that's already there and use that. And it could be your children or your grandchildren who are the first humans to set foot on the red planet. But even more importantly, if there is water on Mars and we can find it, humans are not the only creatures that need water. We just heard from Lucas about these microbes that can maybe survive in small pockets of water on Mars. And so if we find the water, we might be able to find life. So that leads us to our second goal, which is finding life on Mars, perhaps. So this is a really big challenge, so really big goal here. I'm trying to break this up into 4 easy sections to tackle these goals. And I did that in the style of my favorite TV show from childhood. I see some fans are out there. This is Avatar: The Last Airbender. If you're not familiar with the show, the premise is that the hero has to learn how to control all 4 different elements and save the world. And I realized as I was thinking about my research that actually these 4 ingredients are extremely important for the search for life. So I've broken up the talk into these 4 sections, and we'll start off talking about the air on Mars. So what we're looking at here is the surface of Mars. The horizon is the bottom part of this image in the light orange. And then we have a thick orange haze, which is the entire atmosphere of Mars, which separates the surface from the vacuum of space. But just like Earth, Mars has an atmosphere, but that's about where the similarities stop. Like I mentioned before, the air is extremely thin. So imagine as you climb a mountain, the air gets thinner and thinner. Even the top of Mount Everest, the air is 50 times thicker than the average air on Mars. So very little air to go around, and none of it is oxygen. So we're just out of luck. We won't be able to breathe there. Instead, the atmosphere is mostly made up of carbon dioxide, which is good for some organisms, like plants breathe CO2, but we do not. There's also a small amount of water vapor in the atmosphere. You can think of this like the humidity. If it's more humid, there's more water in the air. And also a lot of dust gets picked up. In fact, Mars will have sometimes global dust storms, where a dust storm envelops the whole planet and it lasts for days or even weeks. So already, just from looking at the atmosphere, we can see there's a lot of interconnection between the different elements. There's water in the air and there's dirt in the air, which brings us to our next section, Earth. Or I guess we maybe shouldn't call it Earth because it's Mars, so maybe I'll just call it dirt or soil, or because I have a chronic case of science brain, I might slip up and say regolith, but it's all the same thing. Well, I want to introduce this starting with a game. I want you to guess in just a minute whether the pictures I'm about to show you are Earth or Mars. What I'm showing, just to get us oriented, is a satellite photo of either Earth or Mars, showing a landscape that was carved by water. We can see a bunch of different tributaries all flowing together into one big river. So, show of hands, who thinks that this is a picture of Earth? Okay. And raise your hand if you think this is a picture of Mars. If you said Earth, you were correct. This is a place on Earth, a bunch of water flowing in together. Don't worry, there's another chance right here. So again, I'm showing the exact same feature. We have a bunch of water flowing together, a bunch of rivers tributing into a giant river. So show of hands, who thinks that this is Earth? All right, who thinks that this is Mars? All right, the low-res photo was maybe a giveaway. And the craters, that's also a giveaway. Maybe I shouldn't say that till the game's over. But so we can see that there are two very similar features on Earth and on Mars. We know that this feature on the left is carved by rivers on Earth, and on right, it's the exact same feature. So there was clearly water once on Mars, but not anymore. Okay, let's play another round. Here I'm showing one of these photos is Earth, one of these photos is Mars. This time, instead of a river, we're looking at a delta structure where a river has flown into a standing body of water like a lake or an ocean. And when it does, it deposits all the sediment from upstream and creates a fan-like structure, kind of like the Mississippi River Delta. Okay, so show of hands, who thinks that Mars is the photo on the left side of the screen? And who thinks Mars is on the right? Okay. Y'all are getting pretty good at this. So what's interesting is, again, we have the exact same feature caused by water on both planets. What's particularly interesting about Jezero crater is that that is where we just landed last year, the Mars 2020 Perseverance rover. And I'll talk more about that a little bit later in the talk. But the rover is currently searching around this delta because we think it might be a great place to find life. An ancient riverbed leading into an ancient lake bed. Maybe there's some fossil evidence or something preserved there. But we'll get to that. Another piece of evidence that there was once water on Mars is actually the color of the planet. So Mars is called the red planet because the entire surface has been oxidized or rusted, the same way that if you leave your bike out all winter in Seattle, your chain might develop some rust on it from all the water. But when we look at these dried riverbeds and lakes and deltas, all the water is gone, which just begs the question of where did all that water go? How did so much water disappear? Imagine how much water it would take to rust an entire planet. So to start to answer this, we'll move on to the next chapter, fire, and zoom out a little bit. And since there's no actual fire on Mars, there's nothing to burn, we can also think of this as maybe heat. So though there's no fire on Mars, there is fire somewhere else in the solar system that provides Mars with most of its heat. Does anyone know what I'm talking about? The sun, exactly. So here we have Earth and Mars is a little bit further out from the Earth. And we can see that as you get further and further away from the sun, it gets colder and colder. Just like if you were to move away from these heat lamps, you would get colder and colder and colder. And if we zoom in here, on Earth, we live in this perfect Goldilocks zone where we can have all kinds of water. We can have liquid oceans, we can have clouds up in the sky. At the North and South Pole, we have ice caps. But Mars, which is further away and colder, it has ice caps we can clearly see from space, but not much else. You would think that because it's so cold, it's below freezing for most of the year, that all you would get is ice and nothing else. Except I wouldn't be here if that were true. I'm here to tell you that there is actually something happening at the surface that can let liquid water exist in very small amounts. Which brings us to our fourth chapter. So to think about how water can exist in such a cold and frigid place, let's transport ourselves back to winter, up in the mountain passes maybe, when there's a major snowstorm and the roads freeze over completely. How do we thaw out the roads and make it safe to drive again? We add salt, exactly. So adding salt to ice causes the ice to melt into salty water. The reason is that salt lowers the freezing point of water and allows it to stay liquid even at colder and colder and colder temperatures. And you know, we sometimes do this really well and sometimes not so well, like this photo, it's a last snowstorm. But what's interesting about Mars is that we don't have to spread the salts ourselves. The salts are naturally occurring all over the entire surface. And you might, when I say salt, you might think about table salt, But there are other kinds of salt too. For example, you might have heard of Epsom salts, which is just a fancy name for magnesium sulfate. There are also nitrates, which we use in fertilizers, and perchlorates, which we use in flares and fireworks. All of these salts have been found by rovers and landers, just naturally occurring on the surface, which is pretty weird. So these salts can actually form liquid water in a process known as deliquescence. If you've ever left table salt out on a warm summer day, you might have noticed that it starts to get clumpy and sticky. What's happening is that the salt is pulling water vapor out of the air and starting to dissolve into a salty brine. And that's exactly what we're seeing in this video. We have concentrated balls of salt that are they like water so much that they're pulling it straight out of the air to the extent that they're dissolving almost entirely into little bubbles of brine. And this process is happening on Mars today, in the dirt, which is what makes it so exciting. It's the one way that we can have liquid water that then stays liquid because the salt lowers the freezing point. So to recap what we've learned so far, despite cold and dry conditions, water can exist on Mars today because of the humid air, the salty soil, and the sun's heat. So to use that knowledge, let's ask two even bigger questions. How much water is there on Mars today? And could that water actually be useful for life? And you can think of this as the part of the story where the character learns to control all four elements, but instead of saving the world, we're just going to design a really cool experiment. And so this is an experiment I've done in the lab at University of Washington. I've taken my 4 different elements and added them all together in a container. I like to think of it as having a little piece of Mars in a jar. So I add in my thin, humid air, some salty, rusty dirt, some temperature that I can control with the knob, and the water through either humidity or through salty solution. And it's basically like having a little knob, and I can adjust the knob for each of these parameters to change a whole bunch of different conditions and simulate all these different conditions that might happen on Mars, and study what happens to the salt and the water there. So to walk you through my process a little bit, we start with the air really low. Like I mentioned, the air on Mars is extremely thin. Then I can add in salts and see what happens is that salt, just like we saw in that video earlier, it pulls the water vapor out of the air and starts to dissolve into a brine. Then if I change the humidity, maybe add some more water vapor into the air, even more water starts to dissolve into the soil. The last part of the experiment, I change the temperature and I crank it down to extremely low temperatures. There we go. To see how cold can these little brines get before they freeze solid. Because life needs liquid water. It's not as happy with ice. So I find the point where that all changes to ice. And what I've learned from these experiments is that Mars's dirt is a lot wetter than we once thought. But the next question is that water actually useful for life? Or is that just, great, you have a little salty dirt on Mars? And the reason we care about whether this could support life is because we have rovers up there right now exploring Mars. And if there's life up there, we want to know. We want to avoid a situation where maybe we didn't sterilize the spacecraft properly and there's maybe a hitchhiker on board that might act like an invasive species and outcompete Martian life. We would hate for that to happen. So we really want to know, could these brines support life? And to do that, I have this scale here that goes from 0 to 100% of how salty is your water. At the very bottom at 0%, it's pure salt, just dry. There's nothing that can live in it. At the very top, we have pure fresh water, think babbling brook in a mountain, fresh off the glacier, something like that. So think about now the Dead Sea, which is one of the saltiest bodies of water on Earth. It's called the Dead Sea because it's so salty that no fish can live there, no plants can live there. So it basically looks like nothing can live there. Just shout out some numbers. Where do you think the Dead Sea falls on this chart from 0 to 100? Okay, if you said about 67, you were the closest. So even one of the saltiest bodies of water on Earth only gets down to about 67% on here. And if you scooped up a bucket of water from the Dead Sea and looked at it under a microscope, you would actually see that there's still stuff floating around in there. It's not totally dead. It's just the life is too small for us to see with our naked eyes. But as we get saltier and saltier, there is an absolute limit for how salty life can be before nothing can survive. And that's at about 60% here. Anything below that, life just doesn't have enough water to do its basic functions. So we've never seen Earth life been able to reproduce or grow at conditions below 60%. So thinking back to my experiments where I created brines in the lab, where did those fall in this diagram? I found that mostly they fell below this threshold for life as we know it, meaning that for most of the year and under most conditions, brines on Mars would probably not be habitable for Earth life, which is good because that means it won't be very easy for us to spread contamination there accidentally. But there are certain conditions where the brines were above this threshold, and we could have conditions for life. Or it could be that microbes on Mars are unlike anything we know of, and this threshold for Earth life just doesn't apply. Maybe they are very, very happy to live in salt. We just don't know because we've never actually found anything yet. So if the briny soils are completely devoid of life, then maybe we could use that for future human exploration of Mars. And to explain how we might be able to get water from this, if you have a salty soil, you can't really drink that, so you'll have to extract the water somehow. You might use heat to evaporate the water, leaving behind the salt in the dirt, and then that water vapor can be recondensed out into water, which our future human explorers on Mars could use to survive, which is pretty cool. Okay, so that's everything that I've done in the lab so far. But that's great, it's just in the lab. What about actual Mars, right? Let's get out there and actually test it. And so what I'm showing here is the Perseverance rover, which I told you we'd come back to. I am on the science team for one of the instruments on the Perseverance rover. I work on the Pixel instrument, which is short for the Planetary Instrument for X-ray Lithochemistry. A lot of word salad, but just to break it down, litho means rock, chemistry means studying what things are made out of. The Pixel, you can see here on the robotic arm of the rover, it uses X-rays to study what rocks are made out of. And to explain how it does this, I have an analogy. If you've ever had glow-in-the-dark stars on the ceiling of your childhood bedroom, or maybe in your current bedroom, whatever, it works they're pretty much the same way. You shine a light on the glow-in-the-dark star, it takes in that light, and then when you turn the lights off, it re-emits that light in a process called fluorescence. If you have a camera, you can then take a picture of those glow-in-the-dark stars and see, oh yes, they are there, and they're glowing in this color, and I know what they are, they're glow-in-the-dark stars. So Pixel works in the same way, but for any kind of different rock. The Pixel instrument is up here, this white box, and here I'm showing rocks that fluoresce in a color that we can see. But instead of visible light, Pixel shoots out X-rays, and the rocks bounce back light corresponding to that X-ray. And they might not be in a color that we can actually see, but Pixel is better than the human eye, so it can actually pick up all these different colors that are outside of what the human eye can see on its own. So they might not glow as fantastically as this, but to Pixel, that's basically what it sees. And what's great about this is that every single element, and here I mean elements like on the periodic table, every single element glows in a very, very specific color. So by Pixel seeing what color the rock glows back, it can tell what that rock is made out of. And here I have a picture of Pixel actually in the field, in action. We see the robotic arm is hovering over a rock here on Mars, and I have a little diagram on the right-hand side to explain what's happening. This was actually just a few days ago. So this is a very much an active mission that is right now doing things on Mars. And you can keep track of it if you just Google Mars 2020 Perseverance rover. Every day, images are sent from the rover, directly published straight online. And that's where I got this picture and many, many more. So if you're interested, you can look that up. But basically, the way that Pixel is going to work is that it shoots the X-ray at the part of the rock, and that rock is going to bounce back some fluorescence. And based on the fluorescence that comes back from that rock, Pixel can see, oh yes, this rock is made from iron and silicon. But what makes Pixel cool and new is that it can do this many, many times across a single rock and get a really good map of what that whole rock is made out of. So maybe it moves to a different spot on the rock and does the same thing over again. But this time it detects sodium and chloride, which you might recognize, that's the formula for table salts. So we can see that if Pixel sees a rock with salt in it, then we can go back to my experiments from the lab and see what were the conditions like on Mars at that time, what is the salt that is being detected, and what does that say about the water that's there and its ability to possibly hold life. Overarchingly, sorry, that's not a word. But beyond just looking for salts, Pixel also has the goal of searching for life on Mars. And I don't have any exciting announcements to make at this talk because Pixel is, or the Perseverance rover is so new. It's only been on Mars for about a year. But with any luck, we'll have years and years and years of more exploration to do with this robot. So definitely stay tuned for more exciting discoveries as they come in. And just to wrap up, I wanted to talk about something that's really important to me. Oh no, it's good. It's supposed to do that. Yeah. I wanted to talk about something that's extremely important to me, but it's often overlooked in planetary science and astrobiology. You know, we just heard from Lucas that we sent a robot to Enceladus to scoop up some of the water there. I told you that we sent robots to Mars to look for life. And in the popular media, you might hear people talk about sending humans to Mars one day, colonizing it. And I want to pause on that word, colonization, because it's something we don't really think about a lot in planetary science. You know, tech billionaires might talk about colonizing Mars, and we might read about it in sci-fi books, and it's really entered in our popular imagination as the common sense next step for our Mars program. But I want us to stop and reflect on the history of colonialism here on Earth. So I am very worried that one day we will just take the colonial practices that have built this country and just kind of export that same model into outer space without learning from any of our mistakes. I really think that it's important to study history, study what we did right, what we did wrong, learn from that so that we aren't just blindly stumbling forward, continuing to make the same mistakes again and again and again. If we go to Mars and we discover life, and we discover some valuable resources, are we going to just extract that, trample over that life, and not worry about anything? Or are we going to stop and think ahead of time about how to appropriately explore and settle maybe Mars? So the good news is some scientists have started thinking about this. This is a white paper published recently about ethical exploration and anti-colonial practices in planetary exploration. And the scientists laid out a bunch of ideas for steps that we can take now as we prepare for our future in space. Just to give you some brief summary, environmental stewardship, thinking about how we're going to be interacting with these environments. Are we going to be polluting them, contaminating them with Earth life? The moral consideration for microbial life. No matter how big or small life is life itself valuable to us? What is the value of it? Regardless of whether it's intelligent or whether it looks like us, what do we owe to life that arises on other worlds? And lastly, the profit systems that we have in place and establishing regulations so that we're not just going to Mars, bulldozing everything and taking what we need and thinking about the consequences later. But the problem with this is not a simple solution. I think this has really become something that's become part of the popular imagination at this point. And it's not going to be scientists who are making these decisions. Eventually, it will be private industries, it'll be governments. And I really wanted to bring this up with you all today because I think it's an important thing to start having these discussions now. Because it's too late to turn back the clock and prevent the harms of colonialism on Earth. But we're born at just the right moment where we can break the cycle and move into space with a new model for how to interact with different environments. And so I've coined a term for this. I call it exovironmentalism. An exovironmentalist is someone who advocates for the protection and preservation of environments and possibly life on other worlds. So I'm hoping today that you will all start thinking maybe like exovironmentalists, and considering how to, as we go forward, create a more just and equal world for us in outer space. Thank you.
All right, I may use the weird mic here for a second. Thank you, Andrew. Excellent talk. We have time for questions. So if you have a question for Andrew, I think we've probably got time for 3 or 4 of them. So I'll go ahead and let you choose whose questions to answer. Please repeat the question so that the that the live stream gets it.
Sure thing. Here in the middle.
But we also have a history of sending robots over and letting them decay there. So we're already including another planet. I was wondering what your thoughts were on that.
Yeah, so to repeat the question, we're already sending trash to Mars. Eventually robots will break down and we don't bring them back when they do that. So what are my thoughts on that? It's a difficult moral question because recently we started getting pictures back from Perseverance rover and we found the entry stage. We found the parachute that was just sitting there on the surface of Mars and it will be there forever. There's nothing to break it down. We have to weigh the pros and cons, I think is how I think about it. The amount of science that we are getting back and the amount that we're learning about not just Mars, but our own planet and what our planet was like early in its history. It's maybe worth that trade-off of a parachute sitting on the surface. But that's okay for maybe like a few missions, but as more and more people get the ability to go to Mars, that is something we're gonna have to think about. If everyone's launching their rover to Mars and then just leaving it there to decay, what impact does that have on the environment? And is there a way that we can mitigate that? These are questions that we're gonna have to address in the future. Yes?
If the soils and such are very, very salty, what can we grow there to sustain us once we're there? The second question is, if you're against the extractive process, what do you use to build the environment that you're going to live in once you get out of it?
Okay, so the first question was about the salty soils. What can we actually grow in the salty soils? I wish I had an answer because I'm not actually the biologist. But I did see a study recently that they were able to grow some kind of plant in moon dirt, in actual rocks they have returned from the moon. So I don't think it's a stretch at all that one day we will be able to grow something in Mars's dirt, despite all the salts. And even if not, we can remove the salts maybe first and then use the dirt. And then the second question, can you remind me?
Benignly extract enough to build an environment that you're going to live in once you're there.